Good. Well, good morning, everyone. Today I have the pleasure to initiate this last public presentation from the OIP project, which stands in, for Open Innovation Photonics for Northwest Europe. But of course, it's broader than the Northwest only. It's for full Europe and beyond. So I would like to get started. I will give you an introduction of what we have done in these last years. So I will, it's a short presentation. It's about what were the project objectives. So what were the objectives? Where are we? What was the context? So meaning indium phosphide integrated photonics, and where are the contributions that we have done together with the consortium in terms of moving the technology forward, because it's always an endless technology development. And what are we doing in concrete to support SMEs? This is the map of the consortium. So it is a rich cluster, I would say, consisting of research institutions, but also clusters for photonic innovation and companies. Going from small SMEs, basically small companies, to very large companies. Perhaps the large one we have here is Axtron. As you might know, they are a market leader in epitaxy and CVD systems. And the idea was basically to develop technology based on indium phosphide and the packaging technologies to support the specific applications. So the objectives were to set up an open access pipeline for indium phosphide integrated photonics, validated at an increased TRL level, with improved throughput and cost, provide technology support to SMEs that were looking to mature their PIC-based products through an open collaboration, or semi-open. Doesn't mean that they are collaborating with the full consortium, but they are collaborating with specific partners that add value to their products. And as an end goal, as a target, to establish an open innovation environment for PIC technology in development in Europe, which is a collaborative ecosystem where researchers, fabs, equipment, manufacturers, and SMEs can collaborate together. And on the hardware part, also to have this collaboration to define and develop state-of-the-art equipment and fabrication methods. Now, stepping back a little bit of what is the philosophy of generic indium phosphide integrated photonics, and it is that once you define basic building blocks that can be passives or actives of different types, similar to electronic integration, you can combine them and do a complex electrical photonic circuits in this case. The big advantage of indium phosphide is that you can integrate both passives, but also a diversity of active components, meaning optical amplifiers, lasers, modulators, detectors, and more. And you can integrate all of them into the same type of substrate, and you can fabricate it at the same time. And this is really the strength of indium phosphide to date. What you see here is just a different cross sections of different types of waveguide structures of the devices that I mentioned. And when you look at the design cycle to make a product, it looks roughly as shown in the slide. So everything starts with an application idea from a user that then has access and carries out the design in a specific technology, which is later fabricated, packaged, and product development done. There is testing in different phases of this product development, of course. And in the OIP project, our focus was to help to bridge, from the fabrication to packaging and product development mostly. As 5 years ago, when we started the project, the first phases were already, semi-mature. They were there, available, but we saw that several SMEs were struggling to really bridge these gaps, and in that sense, OIP targeted to contribute to those specific gaps. When looking at the TRL scales, OIP targets were to support these mid-TRL levels, which are often overlooked, going from TRL 5 to 6, 7, where the main hurdles are reliability, cost, and scalability of the manufacturing of the components. So we wanted to have an impact there, and I think we achieved it at some extent. The project phasing was done in these 3 stages. So initially we started with an industrial research phase where we defined the equipment specifications, the specifications of the validation designs, and we started to do process development as soon as we could. Then we went to a validation phase where the new equipment was introduced into the pilot line flow. The photonic ICs were validated by the internal partners of the consortium, by the partner SMEs. And then later, the idea was to have this open access mature technology offer, where the pilot line is fully operational by the foundry, in this case, Smart Photonics. And the external SMEs, external to the consortium, could already get access and be supported. And of course, the idea was to have this phone service with an increased TRL level. Yeah. And of course, it's a continuous reinforcement cycle. All these chip technologies don't have a specific end. I mean, you work on a node, of course, you release it at some certain generation, but then the show must continue. So there are different corners to this continuous development cycle, but OIP specifically contributed to these 2 parts. So developing full photonics ecosystem and also accelerating the scale-up process of the manufacturing technologies. So these are perhaps the 2 main parts where we contributed. And specifically into several aspects. One is the front-end fabrication chip fabrication technologies, which we call it the front end, and then the back end as well. For the front end, as you might know, the fabrication of a photonic chip is a complex process that lasts a few months, and it starts with growing the epitaxial, the material epitaxially, then defining waveguides, doing isolation, passivation, planarization, metallization, and more steps. So it is a complex process. And in OIP, we contributed mostly to the initial phase of this fabrication, mostly from the epitaxial point of view, and also etching of semiconductors, deposition of dielectrics in 4-inch wafers. So we contributed to make this transition from 3-inch manufacturing to 4-inch manufacturing, looking to improving uniformity, reproducibility, and scalability of the manufacturing of photonic chips. And in the next presentation, Alessia will discuss more about this from the front-end perspective. Then from the back-end, packaging technologies, also our partners, Tina National Institute and VUV, they work to improve, their own technologies for packaging of photonic chips, but also to come up with some new innovative solutions, mostly from the freeform optics side. So some new structures that can add a specific functionality to the chips and to the chips in a package. And lastly, we are also busy supporting SMEs. So we established a framework for vouchers. We granted 6 innovation vouchers to SMEs that are active in different fields, from the medical to LiDAR, communications, quantum, as you can see the names of the companies in the slide. And the project comes to an end this week, but the support to these SMEs will continue even after the project. And that brings me to the end of my talk.
Thanks for the introduction. Hello, everyone. So my name is Alessia Senes. I'm R&D Program Manager at Smart Photonics. In the next few slides, I will tell you something more about the front-end pilot line. So you already heard about one of the main goals of the project is to create an open innovation infrastructure, including a manufacturing pilot line for PICs to facilitate the broad uptake of PICs by SMEs in their products. The innovation of the manufacturing processes is focusing on 3 main steps: the epitaxial growth of the basic PIC material, the precision deposition of dielectric layers on the basic peak material, the dry edge performance improvement of the selective removal of layers. And for each one of these 3 steps, in the project has been both a new tool, a new reactor that has been installed and released. So all the new tools for these 3 main steps have been installed and released for 4-inch production, and this allowed to improve the quality, increase capacity of the pilot line. And of course, this could only happen because we had a very good collaboration within the consortium between project partners, but also with the tool manufacturers. The first tool that has been bought and installed in the project is the Extron epitaxy reactor. And then we have 2 more tools from SPTS, the PCVD reactor for dielectrics deposition and the ICP reactor for dry etching. And in the next slides, I will tell you something more about these 3 tools. About the Extron epitaxy planetary reactor, this brings several advantages. The first one is the increased capacity. So with this reactor, it's possible to work on 12 4-inch wafers per time. It has a robot arm for automated wafer transfer, so cassette loading, and this increased productivity, reduced particle contamination, reduced handling, and this means also reducing probability of wafer breakage, and so improving yield. This reactor also allowed for improved process control. In particular, precursor injection and temperature can be very stable. So the process can be finely controlled and can be very stable. And due to this, it was possible to achieve high uniformity, both at wafer level, but also at wafer-to-wafer and run-to-run level. Here you see the PL wavelengths across the 4-inch wafer. And you can see that the PL uniformity is very good, less than 2 nanometers across the whole wafer, centered around the target wavelengths. So this is in-wafer uniformity, and here you see a graph that shows the PL for the average PL for each one of the 12 wafer in the same run that are deposited together in the reactor. So this tool really allows high uniformity on wafer and wafer to wafer. The second tool that has been bought and installed in the project is the PCV reactor from SPTS. This is the use of electric layers, in particular silicon nitride and silicon oxides. It gives high deposit rates, 135 nanometer per minute is what we can use. It gives a high layer uniformity and repeatability. And also the refractive index uniformity and repeatability is within specs. So at the beginning of the project, we set some specs for the different, and these specs are have been achieved for this tool, for this reactor. Here you see a map with the layer thickness across the 4-inch wafer, and you see that the non-uniformity within the 4-inch wafer is 2.2%. In the second graph, you see the layer thickness of layers deposited from different wafers, so from different runs. And you see also the non-uniformity wafer to wafer is 2.7%, so it's very good. The third tool that has been bought and installed in the project is the ICP reactor from SPTS. Also here we can achieve a high etch rate. We use up to 385 nanometer per minute. This reactor allows for high uniformity in wafer and wafer to wafer, and the product parameters such as selectivity, percentage lag, micro trench, angular roughness are comparable to the 3-inch process and are all in spec. Then in the project, not only new tools were bought, bought and installed, but these tools also allow for improved processes, enabled improved processes. For example, what we did as Smart Photonics, we developed a new way to etch the semiconductor to create our waveguide structures. And we moved from the previous slow cyclic process to a fast single etch process. The automation is done by using an endpoint detection, and this technique uses the epitaxial layer to automatically determine when to stop the process. We also developed new chemistry and new integration scheme that allows for etching the same material simultaneously all over the wafer, and this increases automation volume production. So as advantages enabled by process improvement and enabled by the new tools. We had the increase in cycle time related to the process related to this new tool of 10 times faster. And we also have the reduction of a wafer handling that is now 3 times less. That of course means less particles, less possibility of wafer breakage, and higher throughput. Now, how are you using the pilot line within OIP4NWE? Victor just mentioned the voucher scheme offered to SMEs. In the front-end pilot line served 5 SMEs that are using our pilot line. And something nice that we did in this project together with the voucher winners was the support from design phase. So when the SMEs approached the project, the voucher winners, we had early discussion also on packaging and optics that were included in design phase. So this is very good because the chips can be packaged directly at the end of the manufacturing steps. We also serve the 3 validation partners in the projects. These are Embryonics, VTech, and Photon First. The project was in the first phase of, we benchmarked the initial technology. So the pilot line that we had at the beginning of the project, the Smart Photonics on 3-inch. And in the second phase, we evaluated together with the validation partners part of the project, we evaluated the improvements of the technology after the introduction of new processes and new tools. A nice collaboration that we have is with the validation partner Photon First. So Photon First big designs were fabricated on both 3-inch and 4-inch. The 4-inch actually is still ongoing, but they used the new tools and the new processes. At the beginning of the project, for all the validation runs, key performance indicators were defined. There were validation tests. As Smart Photonics, we did on-wafer measurement on the customer designs of Photon First, and they also made, when they received the chips on the singulated dies, they made electrical and optical measurements on their automated die tester that allow for statistical data and relevant information also about the process stability. The main achievement with the validation partner Photon First was the increased optical response of the circuits. The goal defined at the start of the project has been achieved, but also exceeded even 50% beyond targets. And here a nice quote from Photon First. You can read more in the success stories of the project in the OIP4NWE websites. Within the OIP4NWE framework, Photon First introduction of a next-gen fiber optic interrogator marks a significant advancement, emphasizing its commitment to enhancing industry applications and setting Europe's position in the competitive global photonics arena. So we had a nice collaboration with Photon First and the other validation partners. Now, maybe you are wondering, how can you use the pilot line? You can contact Smart Photonics at sales@smartphotonics.nl, or you can also check our NPW offering in the Smart Photonics website. Conclusion of my talk. So what I explained in the past 10 minutes, the front-end 4-inch pilot line is up and running. Then in this project and in the last period, we installed the new tools and released them for 4-inch production. This allows for increased capacity. The tools are cassette-based. This increased throughputs and quality. We improved, thanks to this tool, we improved process control and automation and reduced the particle contamination. The transition from 3-inch to 4-inch production is now ongoing. So at Smart Photonics, we are not starting, the new batches are starting on 4-inch and not on 3-inch anymore. The good collaboration between the project partners is really an highlight of these projects, and this allow the ecosystem to accelerate the transition to 4-inch manufacturing. This was the end of my talk. Thanks for your attention. Thanks for listening.
All right, thank you very much, Dirk. So indeed, welcome everybody. I'm Jurgen van Erps. I'm a professor at Brussels Photonics at the Vrije Universiteit Brussel, and I will cover today the optics, the external optics part of the back end of the PIC processing. Now, one of the things that is typically encountered when packaging photonic integrated circuits is that you have to interface them with optical fibers, for example, or other ways of interfacing them with the outside world. But if you look at a standard optical fiber, the mode field diameter will be typically on the order of 10 micrometer. And that is much larger than the typical mode field diameter of the different waveguides on photonic integrated circuits. And within OIP4NWE, we're focusing on indium phosphide waveguides. And there you see that the mode field diameter will be close to 1 micron. So you have a 10 times mismatch between the mode field diameter in the fiber and in the on-chip waveguide. This mode field diameter mismatch typically means that you have some losses when you're connecting the fiber to the chip. So one way of taking care of that or reducing those connection losses is to use lensed fibers. So this is a typical commercially available lensed fiber where a lens has been polished directly on top of the glass fiber. And then you position the fiber at a certain distance from the chip such that you have a small air gap between the two. But if you're positioned in the focal point of the lens, then you will reduce the size of your mode field coming from the fiber and couple to the chip more efficiently. Now, in order to come up with a solution where you can very well control the mode field diameter at the output, let's say, is to look at mode conversion down tapers. And that's one of the developments that we have done on our side within this project. Here you see a linear down taper where you gradually decrease the size of the waveguide coming from the fiber down to the connection point with the chip. And you can really design your down taper in order to perfectly match the mode field diameter of the chip to which you want to couple. We have then been using a 3D nanoprinting process based on 2-photon polymerization to print those structures directly on top of optical fibers. So here you see them printed on a plain substrate, and this is the linear down taper on a glass substrate, but we can directly print them on top of the fiber such that we have an excellent alignment of the down taper to the center of the fiber, and then we can, couple to the chip with a physical contact. So that's an additional advantage compared to a lensed fiber where you always have this small air gap between the two. In case you're using these down tapers, you can actually make physical contact between the down taper and the chip. Now, in order to reduce some of the length of these down tapers, you can make certain variations. This is a non-linear down taper, which is then shorter to achieve the same functional performance. But as you can see, this is kind of a step index waveguide surrounded by air, so there's some fragility in the device. So to make it more robust, we can also make microstructured variants of this based on effective index guiding and having an array of air holes surrounding the core to protect it from environmental conditions. So, and from our various measurements, we've seen that we can gain up to 1.4 dB per facet when using these custom-made down tapers on the fiber. These numbers are for the indium phosphide PICs in particular. All right, the second development, what you see nowadays strongly in the field of photonic integrated circuits is that people are using different material platforms to exploit their pros and cons. So one of the advantages of the indium phosphide platform that Victor mentioned is that you can do actives on these chips. But if you look, for example, at silicon nitride, you can make much more low loss waveguides, let's say. So in many applications, people are trying to combine the best of both worlds or best of three worlds, and then heterogeneous integration of trying to connect different photonic integrated circuits built on different material platforms can become handy. And towards that aspect, we've been looking at optical interposers that are also fabricated through the same 3D nanoprinting process. So in this case, you see that demonstrated for a fiber-to-fiber application, but it could as well be used as a interconnect structure between the PIC embedded waveguides, where the PICs would be consisting of different waveguide platforms. And you see that we can here again introduce these mode conversion down tapers in order to also be able to make very tight bends in our waveguides And we also are not limited to a horizontal plane. We can also do out-of-plane bands to connect towards 3D structures and so on and so forth. So also this is a pretty interesting development that was resulting from the work within the project. More in general, also in the packaging slide that Victor showed earlier on, you oftentimes also just want to interface with the outside world or to fiber arrays using micro lenses, micro optics. So also in this case, it's possible to custom design your optics to maximize the coupling performance, and you're no longer limited with this 3D nano printing technology to spherical or rotationally symmetric aspherical lenses. You can really do free-form optics to really maximize the optical performance while minimizing the size of the part. And once again, you can do that on a planar substrate, as you see illustrated here. You can, put them in a 2D array as well, where you position the lenses at random, let's say. Yeah? So you have really all freedom. And you can also directly print the optics on an optical fiber. And so in this case, this was a lens that generates a collimated beam for example, expanded beam connections, where you want to increase the tolerance for misalignments in the packaging process. This can be of great help. One step further, you can also look into the realm of diffractive optics. And so in this case, we've demonstrated a structure that allows a 1:7 split of an optical beam. And so you basically see what is projected on the screen here on the right. So we have one single mode optical fiber, then a beam expansion up taper, and on top of the taper, we have a diffractive optical element, which then splits the beam into 7 different spots. And then after a certain propagation distance, you achieve the distribution you want. And so also there, advanced functionalities become possible and can be integrated in a very small way. And if you see, it's again printed on the optical fiber itself. So the diameter of the fiber here is a standard 125 micron diameter. More recently, we've been looking at meta optics, so meta surfaces where you basically represent the lens functionality by making very small arrays of high aspect ratio pillars, which are typically made with electron beam lithography, but then you are limited to one height across the structure. And again, we exploit the advantage of the full 3D freedom of 3D nano printing to enable arrays of nanopillars, which have also got varying heights. So we can again optimize the optical functionality. Now, of course, 3D nano printing is a very nice process for prototyping and small scale production, but as was mentioned earlier on, we also want to look at going to higher TRL levels. So in the validation use case that we've done with embryonics, we first developed some micro-optics interconnect structures, and after the design, we made them with 3D nano printing. And then when they were, let's say, optimally performing, we made the transition towards upscaled production. So in this case, you see an array of 8 micro lenses together with a 45-degree mirror at the bottom, which were produced by micro-injection molding. So you can really scale the production towards thousands, 10,000s, 100,000s, maybe millions of parts without too much trouble. And so you can really make a lot of components at a low cost. These are replicated in a thermoplastic polymer, in which you have, again, a large choice of materials depending on the application that you're targeting. So this is going from prototyping towards higher TRL levels. And then with Photon First, finally, we've been looking at advanced versions of these down conversion tapers. So in the indium phosphide PICs, you often see that the waveguides are coming to the edge of the chip under an angle. And of course, that means that you would either have to position your fibers also under an angle, which then complicates the packaging, again, especially if you want to connect more than one fiber, or in other words, arrays of fibers, because then you would at some point, just hit the chip. So we've been expanding the concept of the down tapers by including the required angle on the end facet of the down taper in order to match the angle under which the light is exiting the photonic integrated circuit, while still allowing physical contact and orthogonal connection to the chip. So this is one of a more recent developments. So we were still working on finalizing this performance. But this, I hope, gave you a good overview of the backend optics, or the interfacing micro-optical components that we can provide, really customized in order to maximize the optical functionality. So if you want more information or want to make use of the pilot line services, get in touch with me and we can discuss your application. Thanks a lot for your attention.
Let's start. Can you see my slide there? Yeah, okay. So thanks for the introduction, Dirk. Welcome, everybody. My name is Mark Rensing. I'm based in Tyndall National Institute at the Photonic Packaging and System Integration Group. And I'll just present here on some of the work that we've carried out in the Interreg OIP pilot line with VUB and Smart Photonics and TUE. So I'll give some of the examples of the services that are available, an example of the voucher execution scheme, and then also going forward, the services that we'll be offering within the pilot line. So during the pilot line project, Tyndall built up and developed its back-end optical packaging capabilities by purchasing an FL300 fiber alignment system from Ficantech. This system uses advanced machine vision and pattern recognition algorithms to enable fully automated alignment and attachment of optical fiber arrays and micro-optic components to PICs. These fiber arrays and then micro-optic components then can be secured to a PIC or a substrate using UV curable epoxy. So with this system, we can achieve high packaging and assembly yields and as well as high throughput times. We already have well-established and developed electrical packaging capabilities, and these are also available through the pilot line. And a number of wire bonders are used for making electrical connections between devices and substrates. So two of the most popular wire bonders we would have would be a gold ball wire bonder with wire diameters ranging from 18 to 30 microns. And this particular tool has been modified to allow us to apply gold stud bumps onto individual die. And these can be used then in conjunction with solder ball jetting and flip chip bonding for electrical packaging prototype development. And then we also have a ribbon bonder for RF packaging applications. And solder ball jetting then is it's a common technique used for providing electrical connections between die and substrates. In this case, individual die and wafers, as well as PCBs and ceramic substrates, can be solder bumped using industry standard solder alloys such as tin, silver, copper, also known as SAC 305, or gold tin. Solder sphere diameters are typically about 50 microns in diameter, and then the system then can handle up to 200 millimeter wafers and deposit 5 balls per second. So it makes the system really suitable for prototype and small volume packaging runs. And our flip chip capabilities then consist of a manual flip chip bonder from Ficantech. And this particular system is the Lambda model, which is very well suited for prototype development and small volume packaging runs. And with this system, standard flip chip bonding processes can be supported, such as solder reflow, again using solder alloys, tin, silver, copper, or gold tin. And we can also bond devices to substrate using thermocompression bonding. So the tool is capable of placing die accurately with an accuracy placement of sub 1 micron, and can handle a range of dies ranging from 300 microns to about 16 millimeters. Top and bottom heating then allows us to apply localized heating and reflow to essentially facilitate chiplet integration onto common substrates. And as within the pilot line, then Tyndall's offer has consisted of offering customized packaging solutions based on these standard packaging processes, and where designers have followed design rules, then we've been able to offer small volume packaging requests, typically of less than 5 units or so, We can provide, and we have provided, optical connections using edge coupling, typically using single mode fiber, but we can also support polarization maintaining fiber. And typically waveguides are pitched at standard pitches of 127 micron or 250 micron. And electrical connections then can be supported using flip chip bonding or wire bonding. Packages then can have an active thermal management system consisting of thermoelectric controller or an SMD. And then I suppose going forward for larger volume requests, customers can engage with Tyndall through our PixApp gateway. We will probably be moving away from a little less of the customization, and I'll talk about that, of standard packages we have planned in the upcoming slides. And so as Victor and Alicia and Jürgen mentioned, we ran a voucher execution scheme during the project. And we've essentially, Tyndall was able to use obviously the processes that we have well established and deliver packaging solutions to 6 SMEs across Europe. And here's just one example of that from for photonics startup based in the Netherlands called Amazec Photonics. And we supported the customization design of a packaging solution for their cardiovascular monitoring system. And this is based on blood temperature measurements. So we developed a customized package that supported fiber array alignment to their PIC using standard single mode fiber and polarization maintaining fiber arrays, which in turn were connected then to high-speed photodiodes. And we integrated then into the package an active thermal management system. And so going forward, in an attempt really to reduce the costs and speed up development and assembly times, we'll be moving away from always offering customized packages. And this is particularly needed in an open access pilot line where the focus should kind of really be on standardization. So we'll be offering standard packages for the two common or the two optical interface schemes that we typically see, edge coupling and grating coupling. And these packages themselves use standardized electrical, optical, and mechanical designs to help really reduce the costs and speed up development and assembly times. So for PICs with low number of DC electrical connections, and the package on the left is an offering that we have. This will support up to 50 electrical connections. And then the package on the right then can be used for a larger number of electrical and optical connections. This is the PixApp ECP100 design. For optical interfaces then where grating couplers are used, again, the package on the left is for a smaller number of electrical and optical connections, typically up to about 20 I/O ports. And this essentially is an off-the-shelf PCB that we've developed and is ideally suited for rapid prototyping. The package on the right then is more suitable, a bit more flexible. It can be used for higher optical and electrical connections. And this one's called the PixApp GCP100. So if you'd like to find out more about these packages and access the packaging services at Tyndall, also find out more about the design rules that will support access to these packages, you can contact myself at the email address shown here. And you can also check out the PixApp website, and there's a contact there as well. That's at pixapp.eu.